Okay, let's start with the basics of unit testing. It's all about creating small tests for individual pieces. We call them units of your code. These units could be a single function or method. The idea is to make sure each part works perfectly on its own without needing help from other parts of the program. We want quick feedback, so if something goes wrong, you know right away. And, importantly, these tests should always give you the same results every time. Okay, let's talk about why unit testing is so important. Basically, it's like making sure every single brick in your software project is solid before you start putting them together. We test small, individual pieces of code like functions or methods to verify they do exactly what they're supposed to do. This helps us catch bugs early on, which saves a huge amount of time and frustration later down the line. Plus, writing unit tests actually encourages you to design your code in a cleaner, more organized way. And when you make changes, having those tests gives you a safety net you can refactor with confidence, knowing that if anything breaks, you'll quickly know exactly where it is. Okay, let's talk about what makes a really good unit test. Think of it like this. You want tests that are super focused, atomic, meaning they tackle just one specific thing. They also need to be independent, so running one test doesn't mess up the others. And crucially, they have to be repeatable. Every time you run them, you should get the same answer. Finally, keep those tests fast. And don't forget your tests should be super readable, so anyone can quickly understand what they are checking. Okay, let's talk about test-driven development, or TDD. Think of it as building software in reverse, at least partially. Instead of writing the code first and then figuring out how to test it, you start by writing a failing test that describes exactly what you want your function or class to do. Then, you write just enough code to make that test pass. Finally, you refactor clean up the code without changing its behavior, making sure all tests still succeed. It's a surprisingly effective way to build robust and understandable software. Okay, so let's talk about why test-driven development is such a great approach. Basically, when you use TDD, you write the test asterisk before asterisk you actually write the code itself. This has some really significant upsides. First, it pushes you to think carefully about exactly what your code needs to do upfront. That leads to much better design and more organized code. Secondly, because you're writing tests first, you catch potential problems early on before they make their way into production. Then, having a bunch of tests gives you serious confidence that the code is working correctly. And it's not just about finding bugs. Those tests actually serve as documentation of how your software is supposed to behave. Finally, TDD makes refactoring, changing existing code without breaking anything much safer and easier because you have tests in place to verify your changes. Okay, let's talk about the core process of test-driven development. It's a really powerful approach, and it's based on this simple cycle: red, green, refactor. First, you write a failing test. This is crucial. It clearly defines what you want your code to do. Then you write just enough code to make that test pass. It's tempting to add extra features or complexity at this stage, but resist that urge. Focus on the minimal amount of code needed. And finally, once it's green, you refactor, clean up the code to improve its design and readability without changing how it works. It's a continuous loop, repeating for every new piece of functionality or when you need to tweak something existing. Ready to dive into some interview questions related to this? Okay, let's talk about the difference between unit and integration testing. Unit tests are like checking each tiny part of your code, individual functions or methods, to make sure they work perfectly on their own. They're quick and easy to write because they don't depend on anything else. Now, integration tests go a step further. They test how those little pieces actually work together . So, you're verifying that when you combine them, the overall system does what it's supposed to do. Think of it like building with Lego bricks. Unit tests make sure each brick is good, and integration tests ensure they fit well together to build something bigger. Okay, let's talk about mock objects. Think of them as placeholders for the things your code depends on, like databases or external API. During unit tests, we want to test just our component, not the whole system. So, instead of using the real database or API, which can be slow and unreliable, we use a mock object. A mock is essentially a control version that gives us exactly what we need for the specific test: predictable responses, fast execution, and full control over the testing environment. It isolates our component and helps us ensure it works correctly on its own. Okay, so let's talk about mocks, stubs, and fakes. They all help us test our code in isolation, but they do different things. A fake is basically a simple replacement for something complicated like a database, giving you controlled data without the real connection overhead. A stub just gives you predefined answers when it's called. You're focused on what the dependency asterisk returns asterisk. Then there are mocks. These actively check that your code asterisk actually asterisk interacts with the dependency correctly, verifying calls and arguments to make sure everything is working as expected. Okay, let's talk about dependency injection. It's a really important technique for writing solid unit tests. Think of it like this: instead of your code asterisk creating asterisk its dependencies itself, say, grabbing a database connection or a service object, we give those dependencies to the code from the outside. This makes our unit tests much easier because we can replace these real dependencies with mock versions that don't actually do anything complicated. It isolates the part of our code we want to test, and it gives us complete control over what happens during the test. Okay, let's talk about test doubles. Essentially, they're like placeholders we use when testing a single piece of code our unit. We don't want to rely on the real-world versions of things like databases or external services during these tests because they can be slow, unreliable, or difficult to configure. Instead, we use test doubles. Mocks, stubs, fakes, and spies are all different types of stand-ins that mimic those dependencies' behavior so our unit tests can run quickly and reliably. Okay, let's talk about tools. When discussing your unit testing experience, it's really important to showcase what you've actually used asterisk. There are tons of options out there depending on the language you're working with. For Java, JUnit and Mockito are hugely popular. They help you isolate parts of your code for focus tests. Python users often gravitate towards PyTest and Unitest. Jest and Jasmine are really common in JavaScript, and NUnit and XUnit are strong choices for .NET. And don't forget Go. Testify and GoMock are excellent frameworks for testing Go code. It's not enough just to name them, they'll be ready to briefly explain asterisk why asterisk you found each one useful in your projects. Okay, so when you're thinking about what to test in a unit test, it's really important to narrow your focus. You want to be testing the specific things that users or other parts of your application interact with directly, what we call the public API. Think about methods and properties that are exposed externally. Don't get bogged down in how those functions actually work internally unless that behavior is part of their defined interface. Also, each test should ideally verify just one specific thing, like a single responsibility. And don't forget to think about edge cases. What happens when you give it 0 inputs? What happens when you give it a lot? Testing for errors and how your component handles them is also super important. Finally, structuring your tests using the given when-then pattern can really help keep things organized and ensure you're testing effectively. Okay, let's talk about code coverage. Think of it as a way to see how much of your code base is actually being tested by your unit tests. It's not necessarily about asterisk how good asterisk the tests are, but rather asterisk how much asterisk of your code they cover. There are different types: statement coverage, which checks every line; branch coverage, which looks at all possible outcomes of if or else statements; condition coverage, that focuses on testing all combinations within those decisions; and path coverage, which is about covering every single possible execution route through your code. Most testing frameworks give you tools to generate reports showing exactly what's covered. Remember though, aiming for 100% isn't always the goal. Really well-written tests are more important than just hitting a percentage. Okay, let's talk about a really common interview question: is 100% code coverage necessary? The key takeaway here is that hitting 100% isn't the goal. While it's good to aim for high coverage around 80% or better, what really matters is making sure your tests actually verify your code's behavior and logic. Sometimes, focusing solely on getting every single line executed leads to writing a lot of unnecessary tests, or even duplicating existing ones. Remember, you're testing the what, not just the where. It's about demonstrating that your tests are thorough and effective. Okay, so let's talk about code coverage metrics. They are often thrown around in interviews. They tell you how much of your code is being executed by your tests, which can seem reassuring at first. But the crucial thing to remember is that high coverage doesn't automatically mean you have good tests. It's possible to cover a lot of lines without actually testing important logic or handling edge cases. It also doesn't tell us if our tests are actually finding bugs. It just shows how many lines we exercised. When looking at legacy code, high coverage can actually hide serious problems. So, instead of obsessing over percentages, focus on writing tests that really verify your application's behavior and tackle the areas where things are most likely to go wrong. Okay, let's talk about something super important in unit testing: isolation. Basically, we want our tests to be like little bubbles focused entirely on the piece of code they're examining. If a test depends on other things outside its scope, maybe a database connection or another function, it can become flaky and unreliable. It might pass sometimes and fail others because those external factors are changing. Isolation makes tests fast, predictable, and much easier to maintain. We achieve this primarily by using techniques like mocking, where we replace real dependencies with fake ones that give us the behavior we need without the side effects. Dependency injection is another key strategy, letting a unit receive its needs rather than creating them itself. Think of it like building with Lego bricks. You want each brick unit to work independently and easily connect to others. Alright, let's talk about testing private methods, a frequent interview question. The key takeaway here is that you can't directly test them because they're hidden implementation details. But don't worry, we have some great strategies. Dependency injection is your best friend. Create mock versions of the class containing those private methods and control their interactions within your tests. If the method follows an interface, test that interface instead. And crucially, focus on testing the public methods, these methods called the private ones, so by ensuring they work correctly, you're indirectly verifying the logic inside. Finally, consider using a spy to check how those private methods are being called, without actually executing them. It's all about validating the overall system, not digging too deep into the implementation details. Okay, let's talk about how to deal with those external things: databases, API, file systems when writing unit tests. They can make testing tricky because you don't want your test to depend on something that might be slow or unreliable. The main strategy here is mocking and stubbing. Mocking involves replacing the real dependency with a fake version, a mock object that acts exactly like the real one, but you control its responses. Stubbing is similar, but instead of mimicking everything, you just provide some preset values to the dependency. It's about isolating your unit and testing its logic without worrying about external factors. Remember, fast, independent tests are key, and don't mock everything. Sometimes it's okay and even beneficial to use a real dependency for broader coverage. Okay, let's talk about mocking. Essentially, when we're unit testing, we want to make sure our code works in isolation. Sometimes a piece of code relies on other things like a database or an API. But those real dependencies can be slow and unreliable. That's where mocks come in. Think of them as stand-ins, fake versions of those external components. They let us control exactly how the dependency should behave during our test, which makes testing much faster, more reliable, and gives us a lot more flexibility. Okay, let's talk about testing exceptions. When you write unit tests, it's crucial to make sure your code gracefully handles unexpected scenarios, things like errors or invalid inputs. The key is to arrange a situation where an exception should be thrown, then act by calling the function that might trigger it, and finally, assert that the correct type of exception is actually raised. Essentially, you're forcing your code to fail in a controlled way so you can confirm its error handling works correctly. I often recommend using assertion methods provided by your testing framework. They make this process much cleaner. And don't forget about mocking and stubbing if your unit depends on external resources that could cause exceptions. Okay, so let's talk about parameterized testing. It's all about making your tests more efficient and reducing redundancy. Imagine you have a function that takes different prices and discount percentages as input. Instead of writing separate test cases for each combination, you can create one test method that accepts those values as parameters. This way, you cover all the scenarios with just a few test methods, keeping things clean and easy to maintain. It's like having a reusable template for your tests. Okay, let's talk about a really helpful workflow for writing unit tests. It's called arrange, act, assert. Think of it as your testing process. First, you arrange things. That means setting up everything your test needs to work correctly, creating objects, maybe mocking out some external services, or making sure all the variables are in the right place. Then, you act by actually running the code you're trying to test. Finally, you assert, which is where you check if the result of the action matches what you expected using your testing framework's assertions to verify everything is correct. Okay, let's talk about some common roadblocks when it comes to writing unit tests. One thing that often pops up is dealing with dependency, things like databases or external services. Creating realistic mock versions of these can take a fair bit of work. Then there's the challenge of testing methods that might have side effects, changing global state or affecting other parts of your application. Setting up and cleaning up before and after each test can also add extra code. And as your project grows, keeping those tests updated alongside the changes in your code is a constant task. Finally, it's easy to fall into the trap of testing everything, which leads to really long and fragile tests that aren't actually giving you much insight into how your code behaves. Okay, let's talk about black box versus white box testing. Black box testing is like treating your software as a complete product. You're checking if it meets the requirements from a user's perspective without knowing anything about its inner workings. Think of it as testing how well a car drives and handles. On the other hand, white box testing dives deep into the code itself, examining its structure and logic. It's like an engineer looking at the engine to ensure everything is running smoothly. Both are important for creating robust software. Okay, let's talk about continuous testing and how it fits into CI/CD. Essentially, we're automating the process of running tests throughout our entire development pipeline. Whenever a developer commits new code, the system automatically builds the application and kicks off all the relevant unit tests to check individual components, integration tests to ensure they work together, and sometimes even end-to-end tests to simulate user interactions. If any test fails, the build stops immediately, giving developers quick feedback so they can fix the issue right away. This prevents bad code from making its way into later stages, leading to higher quality software and a much smoother deployment process. Okay, let's talk about how to keep your unit tests organized. It's a really important part of writing maintainable code. First, I like to group my tests right alongside the code they are testing, or in a separate tests folder nearby. This makes things super easy to find and understand. Next, test names matter. I always try to make them really descriptive. Something like test calculate total valid input tells me exactly what I'm checking. And finally, think about grouping your tests into suites based on the functionality they cover, like data access or user authentication, and then within those suites, group related tests together for even better organization. Okay, let's talk about naming unit tests. It's surprisingly important. Don't just slap together a generic name like test method. A good name tells you exactly what scenario is being tested. I recommend using a pattern that includes the class being tested, the action performed, and the expected result. Something like test order processor out valid items returns correct total. The goal is for anyone reading your test to immediately understand what's going on without needing to dig into the code. Clarity really makes a big difference in maintainability. Okay, let's talk about test suites. Imagine you're building a house. You wouldn't just randomly check every brick. You'd have specific tests for the foundation, the walls, the roof, and so on. A test suite is essentially that same concept for your code. It's a collection of related tests designed to verify how a particular feature or part of your application works. These tests are grouped together logically, often by what they're testing, making it easier to find problems and keep everything organized. They share dependencies, meaning one test might set up the environment for another, ensuring everything's ready to go. And because they are well structured, you can reuse them across multiple projects, or even in different parts of the same project. Okay, let's talk about test fixtures. In test-driven development, we want to make sure our unit tests are focused and isolated. That's where test fixtures come in. Essentially, a test fixture is like creating a mini environment just for your tests, a little stage prepared for the act as your code. It handles setting up any necessary data or objects * before * your test runs, and cleans things up afterward. They often involve dependency injection to avoid relying on outside systems that could affect the outcome of your tests. Think of them as helpers that provide consistent, predictable conditions so you can really drill down into what your unit is doing. Okay, so let's dive into regression testing. It's really important for maintaining stability in your software. Basically, after you add a new feature or fix a bug, you want to make sure you haven't accidentally broken anything that was already working perfectly fine. Regression testing is the process of running all your existing tests, especially those unit tests again. Unit tests are like individual quality checks for each piece of code. Regression testing then looks at how all those pieces work together and makes sure they still work together correctly after you've made changes. It's a safety net to catch unexpected issues that could arise from modifications. Okay, let's talk about flaky tests. They're a real pain in the neck for developers and testers. Basically, a flaky test is one that randomly passes or fails, even if your code hasn't changed at all. It's like it has a mind of its own. They can be caused by things like unpredictable external services, race conditions where multiple tests are trying to do something at the same time, or even just timing issues with how quickly elements load on a web page. To deal with them, you need to figure out what's causing the inconsistency, maybe mock out those unreliable dependencies, implement retry logic for occasional hiccups, and most importantly, make sure your test environments are as stable as possible. Okay, let's talk about synchronous versus asynchronous testing. Synchronous testing is how we've traditionally done things. It's like a direct conversation with the application. The test runs alongside your code, and you get immediate feedback. You can step through everything easily. Now, asynchronous testing comes into play when dealing with systems that don't respond instantly, like web servers or databases. It's more like sending a letter. You send the request and then continue on without waiting for an answer. So, we need to handle those potential delays and make sure things arrived as expected. Let's look at some key differences in a table here: blocking behavior, response time, and complexity. Okay, let's talk about how we tackle testing asynchronous code. This is where things get a little trickier than your usual synchronous tests. The main thing to keep in mind is that you don't want to block your tests with long-running operations. You need to make sure they finish quickly. When dealing with promises and async/await, mocking becomes really important, essentially simulating the asynchronous behavior of the code you're testing. This lets you control what happens and focus on verifying the expected outcomes. And remember, when asserting that an async function works correctly, don't try to check its return value within the function itself. Instead, test whether the promise it returns resolves or rejects as it should. Okay, let's talk about assertions. They are absolutely key to unit testing. They're basically the questions we ask our code to make sure it's doing what we expect. Think of them as checks like, is this number really 5, or does this function actually return a string? Most testing frameworks use functions that throw in error if something isn't right, like assert equal to check for equality, or assert true to confirm something is true. We also have type checking and numerical comparisons, all designed to give us clear feedback when our tests fail. Okay, let's talk about mocking databases in unit tests, a really important skill for any software developer. Databases can be tricky to work with because they are complex and potentially slow. Mocking lets us isolate the code we're testing from the database entirely. This means our tests will run much faster and won't be affected by changes in the actual database. There are several ways to do this. First, you can use dependency injection. That means passing a mock database object into your class being tested. Alternatively, you can use mocking libraries like mock or ent-substitute, which provide really helpful fluent interfaces. Or, you can simply stub out the real methods of the database, effectively replacing them with simple implementations that return predefined values. It's all about controlling what your code interacts with to ensure clean and reliable unit tests. Okay, so let's talk about how unit testing fits into Agile. It's incredibly important. Basically, unit tests are like mini exams for your code. They make sure each individual piece of functionality is working correctly on its own. Because Agile is all about quick iterations and feedback, unit tests provide that instant confirmation that you're moving in the right direction. They help reduce risks, improve the design of your software, and really solidify those continuous integration pipelines so things are reliable as they go out for deployment. It's a crucial element to creating adaptable and dependable applications. Let's talk about how TDD boosts code quality. The core idea is that you write your test asterisk before asterisk you write any of the actual implementation code. This might seem counterintuitive at first, but it actually forces you to really think through exactly what your function or class should do, clarifying your requirements up front. Because you have these tests already written and passing, they act like a safety net, immediately catching bugs as you make changes. It also pushes you towards writing smaller, more modular code, which is much easier to understand and maintain in the long run. Unsurprisingly, those tests actually serve as really useful documentation, making debugging significantly faster because you have a clear set of expectations built into your project. Okay, so let's address a really common question about TDD. Does it actually slow things down? Initially, it can feel like adding extra steps to your workflow. You're essentially thinking about what you want to achieve asterisk before asterisk you write the code. There's definitely a learning curve involved for developers new to TDD, and sometimes debugging tests can take some time. But here's the thing, writing tests first forces you to think really carefully about how your code will work, which leads to much better design and less bugs down the road. Plus, those tests actually act as documentation. And if you need to refactor later, having a robust test suite makes that process way safer and faster. So, while there might be a small initial slowdown, TDD consistently delivers long-term gains in terms of code quality and maintainability. Okay, let's dive into refactoring and how it works hand in hand with test-driven development. Refactoring is basically about making your code cleaner and more understandable without changing what it asterisk does asterisk. It's like tidying up a room. You rearrange things to make them better organized, but the purpose of the room stays the same. TDD helps us do this safely because we're always building our code around tests that clearly define exactly how it should behave. When we need to refactor, knowing those tests are passing gives us enormous confidence that we're making improvements and not accidentally introducing bugs. Okay, let's talk about the difference between BDD and TDD. Think of TDD as a very specific coding process. You write tests first, then write just enough code to make those tests pass, and finally you refactor. It's all about making sure your code works correctly. Now, BDD is slightly broader. It's more focused on asterisk what asterisk the software should do, rather than just asterisk how asterisk. It uses a language like Gherkin to describe those behaviors, ensuring everyone, developers, testers, and even clients, understands the expected outcomes. Essentially, TDD focuses on the implementation details while BDD focuses on the user story or desired behavior. Let's talk about the test pyramid. Think of it like building a sturdy structure. You need a strong base to support everything else. At the very bottom are your unit tests, which are super fast and focused on testing individual pieces of code in isolation. Next up is the middle layer, integration tests. These check how different parts of your application work together. Finally, at the top, you have your end-to-end tests. These simulate real user interactions across the whole system. The goal is to have a lot more unit tests than integration and ITWOE tests because they take much longer to run. Using this pyramid helps you prioritize testing effectively and ensure you're covering all critical areas without getting bogged down in excessive complexity. Okay, so let's talk about keeping your unit tests actually reliable. It's super important. You don't want tests that randomly fail just because something changed elsewhere. The key is to think proactively. First, schedule regular test runs like a nightly or weekly routine so you can catch problems quickly if they pop up. Then be really mindful of what your tests depend on. If they're using external services, databases, or API, make sure those are stable and well managed. You might even want to mock some of these dependencies to isolate the code you're testing. Also, clean test data is a game changer. Inconsistent data can lead to flaky results. Dependency injection and mocking really help with isolation. Finally, set up monitoring so you're alerted if your tests start failing more often than usual. Maintaining reliable tests isn't a one-time thing, it's an ongoing effort. Okay, let's talk about snapshot testing. It's a really cool way to ensure your code consistently produces the same results over time. Think of it like taking a picture. You capture what the output looks like at one point in time. Then, on each subsequent run, you compare the original snapshot to the current output. If they match, great. You know things are still working as expected. It's particularly helpful when your code generates dynamic stuff like HTML or JSON, and you just want to be sure it doesn't suddenly start spitting out totally different content while not suitable for complex scenarios. Snapshot testing is a fantastic tool in the right situation. Let's talk about tackling that tricky situation of legacy code without tests. It's honestly one of the most frequent interview questions you'll face. The best strategy isn't to try and rewrite everything at once. That's a recipe for disaster. Instead, we focus on small incremental changes. Start by picking a tiny piece of functionality, then write a minimal test specifically for that section. Refactor the code, making it cleaner and easier to understand, all while keeping those tests running smoothly. As you improve the code, add more tests, really digging into how it should behave in different situations. Think about critical paths and edge cases. Those are key areas to prioritize. It's a slow and steady process of cautious improvement, not a massive rewrite. Okay, let's talk about some common mistakes people make when writing unit tests, things we call anti-patterns. You'll often see large test classes crammed with a bunch of different assertions, which can quickly become really hard to manage and maintain. Another issue is testing how something works internally, like checking if a specific method name exists or using database connection strings in your tests. That makes your tests super fragile. Any small change to the code can break them. Over-reliance on mocking everything can also be problematic. It's great for isolating components, but too much can create a tangled web of dependencies. And don't get me started on abusing test doubles. It's easy to overdo it. Finally, just asserting that an exception is thrown isn't enough. Make sure you are checking the specific type and message associated with it. It's important to think about your overall code coverage too, not just whether all tests pass. Okay, let's talk about unit testing in the context of microservices. Microservices are designed to be independent pieces, and that's where unit testing really shines. Because each service operates as a standalone unit, you can test them completely independently, meaning you don't need to worry if another service is up and running or not during your tests. This gives you super fast feedback loops, allowing you to quickly spot problems within a single service and fix them, which significantly speeds up the development process. And it forces you to think about breaking down your code into smaller, more testable components, leading to generally higher quality code overall. Okay, let's talk about how to tackle testing error handling. It's more than just verifying that an exception does occur. We need to make sure we're testing for the right kind of exception with a meaningful message that helps us understand what went wrong. A key part is often mocking external dependencies. If your code relies on things like databases or services, you'll want to control those during tests. And finally, it's vital to confirm how your application actually handles the error. Does it gracefully recover? Does it log the issue so you can track it down? Okay, let's talk about how we can actually judge if our unit tests are doing a good job. We don't just want lots of tests, we need tests that actually catch problems. One way to do this is by looking at metrics numbers that give us clues. Code coverage tells us what parts of the code are being exercised by our tests, and high coverage is generally good. Test density looks at how many tests we have per piece of code, which can help us avoid making too many or not enough tests. We also want to know if our tests are consistently passing a low pass rate could indicate real problems in the code itself. And then there's mutation testing, which is like throwing little errors into your code and seeing if your tests catch them. Finally, consider the complexity of those tests themselves. Simpler tests tend to be easier to maintain. Thank you for watching.